Every popular belief about black holes, the sucking, the instant death at the horizon, the trapped information, even the famous photo, is either wrong or far more complicated than anyone told you. Documentaries, sci-fi movies, explainer posters, they've all been quietly installing a set of mental models into your head for years. Some of those models are partially wrong, some are completely wrong, and the accurate picture isn't less terrifying than the myths, it's stranger. Let's check what we actually know versus what we think we know. Run through each myth, test it against the physics, see which ones survive. Start with the big one, the one that shows up in every classroom poster and every space documentary ever made. Black holes suck things in. They're cosmic vacuum cleaners, hoovering up anything nearby, pulling you toward them the moment you get close. Sounds right, feels right. It's wrong. A black hole doesn't suck anything. That's not how gravity works, and it was never how gravity worked. A black hole pulls on you the exact same way any other mass does. Gravity doesn't care about density or size or how terrifying something looks. It only cares about mass and distance. If you took the sun right now, all of it, every last ounce, and compressed it down to the size of a city, Earth's orbit wouldn't change by a single kilometer. We'd keep circling a black hole of equal mass in complete darkness, following the exact same path we follow today. The black hole pulls no harder than the sun did. You have to get extremely close, city block distances from the center, before the event horizon becomes physically relevant. Black holes don't hunt, they just sit there. Things fall in because they got too close and couldn't generate enough speed to escape, the same way anything falls toward anything else with mass. Think about a drain in a bathtub. The water doesn't get sucked in. The water falls toward the drain because gravity exists and the drain is the lowest point. The drain has no special pulling power beyond its location. Black holes are the same. Incomprehensibly massive, yes, but not pulling any harder than the mass they contain. Now here's where it gets interesting. Pause here. Think about this before you keep watching. If someone replaced the sun with a black hole of exactly equal mass right now, what happens to Earth? Does it spiral into the black hole within minutes? Does it continue orbiting normally in total darkness? Or does the gravitational disruption fling it out of the solar system entirely? Hold your answer. The physics has already decided. Earth keeps orbiting, normally. Same path, same speed, same year length, just no light. The black hole pulls no harder than the sun did because it's the same mass. Most people predict catastrophe, and that prediction reveals something important. You had a mental model of black holes as active predators. They aren't. They're just very compressed mass. Now you can unlearn that. On to myth 2. The event horizon kills you instantly. Cross that invisible line and you're torn apart, spaghettified, crushed, destroyed at the boundary itself. This is where the physics gets genuinely strange. The answer depends entirely on which black hole you're talking about, and the answer is completely backwards from what you'd expect. For a small black hole, a stellar remnant, the kind left behind when a massive star collapses, a few times the mass of our sun, spaghettification starts thousands of kilometers before you ever reach the event horizon. The reason is this. Gravity changes steeply over short distances near a small black hole. The pull on your feet, aimed directly at the center, is vastly stronger than the pull on your head, which is just a couple of meters farther away. That difference, that stretch, is what kills you. It starts long before you cross any boundary. You'd never even get to the event horizon intact. But a supermassive black hole, the kind that anchors galaxies at their centers with masses equivalent to billions of suns, has an event horizon larger than our entire solar system. Its gravitational pull changes so slowly across human-scale distances that the difference between your head and your feet at the boundary is almost zero. You'd cross the point of no return feeling nothing, no alarm, no physical sensation, no warning. Your doom is guaranteed, but it arrives later, deeper in. The horror starts well inside, long after you've crossed. Size reverses the intuition completely. The smaller the black hole, the more violent the approach. The bigger the black hole, the gentler the entry, and the more inescapable the trap. Here's your second challenge. You have to fall into one of two black holes. The first, mass of 10 suns compressed to the size of a city. The second, mass of 6 billion suns, event horizon bigger than our solar system. Which one gives you a gentler crossing at the boundary? Think about it carefully. Everything you feel about this answer is probably wrong. The giant one, the incomprehensibly massive one. Its gravity is spread so gently across such an enormous boundary that you'd cross the point of no return intact and unaware. The small one would stretch you apart thousands of kilometers out in screaming agony before you ever reached the line. The more terrifying thing is that the gentle crossing makes no difference. Once you're inside the supermassive black hole's event horizon, nothing, no thrust, no signal, no physics gets you back out. You're past the point of no return in perfect physical comfort, and you still have nowhere to go but in. Now, the myth that physicists themselves fought over for decades. Black holes trap everything forever. All information, all matter, all energy gone permanently, destroyed at the singularity, lost to the universe. This was the position Hawking held for years, defended vigorously, and argued was a fundamental feature of black holes. He was confident. He was the most famous physicist of his generation. He was probably wrong. In the 1970s, Hawking worked out that black holes slowly lose energy over time. Not quickly, not in any human time frame, but over timescales so vast they make the current age of the universe look like a blink. The mechanism works at the edge of the event horizon, where particle pairs can briefly form and separate, with one escaping and one falling in. Over an unimaginably long time, a black hole radiates this energy away and eventually, in principle, evaporates. A stellar mass black hole would take longer to evaporate than the age of the universe repeated 100,000 trillion times. Not soon, but not infinite. The bigger point, that radiation may carry out the information that fell in, scrambled beyond any practical recovery, but technically present. Like burning a book and preserving every single ash particle. The information is theoretically still there, but reassembling it is so impossible it might as well be gone. In 2004, Hawking conceded he'd been wrong about information being destroyed. He even paid a bet he'd made. That concession remains disputed. One last question before the final piece. Hawking spent decades defending information destruction. He changed his mind in 2004 and admitted it probably escapes. Was that intellectual honesty from the greatest physicist of his generation, or the field's most famous scientist surrendering to peer pressure before anyone had proof? The information paradox is still unresolved as of right now. No experimental test exists. The leading theoretical idea says information escapes encoded in the radiation, scrambled beyond recognition, but present. Other physicists disagree. Nobody has confirmed it. Decide what you think that 2004 concession means. Then consider, if we can't resolve this about information, what else are we wrong about? The famous photo. You've seen it. The orange ring, the dark center, the glowing halo. Released in 2019 after 2 years of computing by 8 synchronized observatories spread across the entire planet. 4 million gigabytes of data. The most ambitious collaborative telescope project in human history. The result? Humanity's first image of a black hole. Except it isn't. What you're looking at is superheated gas spiraling inward, glowing orange because friction heats it to temperatures that dwarf anything on Earth's surface. Hotter than you can imagine, hotter than the surface of our sun by orders of magnitude. That gas is emitting light. The dark circle in the center isn't the black hole, it's the shadow cast by a region where light curves so sharply toward the center that it falls in. You're seeing a shadow of an absence. The black hole itself has never been photographed. It cannot be photographed. No light escapes its event horizon. It is, by definition, invisible. The real physics replaces the cheap horror with something far more unsettling. Black holes don't hunt you, but you can fall in without noticing until it's too late. The event horizon doesn't kill you immediately, but that's worse, not better, because you're now trapped with no exit and the end arrives anyway. Information might escape, but in a form so scrambled it's functionally gone, and the smartest physicists alive can't agree on whether it escapes at all. The parts everyone fears aren't the dangerous parts. The dangerous parts are the ones nobody mentions. The invisible boundary, the comfortable crossing, and the contradiction at the center of physics that nobody has solved.